All right, welcome back to the last lesson for this week. We're just going to be looking at testing the stoichiometric method. So what this means, like normally if you are doing stoichiometry, as it is kind of mentioned that we're kind of analyzing chemical reactions, so we need to be able to test away that if we are doing a reaction that we're optimizing it and we're actually getting everything that we should be getting out of it. And like all these calculations so far, that you guys been looking at is like how much of this mass is going to be produced. Well, this is all in theory, right? So if the experiment goes right, our assumptions are true, we should be able to collect everything that's there. But sometimes when you're doing an experiment, you don't get everything. So that's why it says here, in theory, the values determined for mass or any other quantity should be the same whether you use an experimental procedure or stoichiometric calculations, but the accuracy of experimental technique is based on comparison between your experimental value, so what you actually collect at the end of a lab, compared to what you predict, and that is your stoichiometric calculations. Because when we do stoichiometry, there's a bunch of assumptions there, but stuff can go wrong, so the reaction might not go to completion. You might spill some stuff. Stuff might stick to the side of glassware. So there's always little tiny things that can happen that will cause us not to actually get everything that we predict. So that's why we have these two things right here. Our predicted value, stoichiometry, our expected what we actually collect at the end of a lab. So one of the things that we're going to do to measure how effective our laboratory techniques are is something called the percent difference. So this is a measurement of how close the experimental value is to the predicted. So a percent difference above 10% is considered to be unacceptable. So we're going to be looking at that, but depending on the lab, we can get a little higher than that, but that's okay. So one thing just to notice as well, the little straight lines up here, this isn't a typo, this is the absolute value sign. So basically that just means no negative numbers. Because when we are doing this right here, so our percent difference, we're getting a percent, we don't want a negative percent because it's just telling us how far we are from the predicted value. So our equation is we get our experimental value minus our predicted over our predicted times 100%. And that should leave us with our percent difference. So, of course, we will need to kind of get just a few little definitions out of the way for a laboratory procedure. So before, during, and after every lab, you must outline your prediction, perform an analysis on your collected data, and then write an evaluation on your laboratory experiment. That is every lab you will do. Now, obviously, with the circumstances that we have right now, we can't really do that. But either way, we will kind of go through them on paper. So words you want to look for, specifically when you're answering stuff on labs, is prediction, analysis, and evaluation. So your prediction is always going to be your stoichiometric calculations. In every lab that you have in chemistry, this is kind of what you're doing. It's like one of them is solving for a concentration. What mass should you produce? So that is this is your prediction that you're trying to get. Now your analysis is determining the actual experimental value. So this is where you're going to have to read the question and figure like, okay, so a filter paper weighed 5 grams before you collected the solid. Afterwards, the filter paper and the solid weighed 25 grams. How much did you collect? Little things like that. So we'll kind of go through that when we get to it. And then finally, evaluation is performing our percent difference calculation or percent yield. And this one right here, we will see later. They'll come up later in the unit. So basically right now our evaluation is performing our percent difference calculation. So let's have a look at a typical experimental design and how we actually go through our prediction, analysis, and evaluation. So example 1, experimental design. So a teacher places 28.0 grams of scandium chloride. So of course scandium chloride is SC2 plus and chlorine is 1 minus. So when we drop and swap, that gets to SCCl2. That is our scandium chloride. Scandium is 3 plus. When in doubt, check your data booklets. So if you're wondering where scandium is right here next to calcium and it's 3 plus. Sorry about that, just kind of almost got that mixed up there for a second. So that will leave us with SCCl3. So a teacher placed 28.0 grams of scandium chloride and 100 milliliters of water. Students add to this a silver nitrate solution. So the evidence, the student weighs filter paper to be 0.59 grams. Students then filter the precipitate and attain a new mass of 78.59 grams. So complete the prediction, analysis, and evaluation of this lab. So what we have right here, this evidence, so this is after the experiment was done, and this is going to help us find the actual. But for our stoichiometry, we're only going to use our experimental stuff. So this is where you are going to be given a lot of different bits of information, so you should just be aware of, are they talking about before or after the reaction? Because everything before the reaction is going to be in our prediction. Everything after is going to be in our analysis, because it's after the reaction occurred, and this is what we actually picked up, or actually what we got. So remember, our prediction is our stoich. So for our stoich, we're just going to follow the exact same steps that we did last time. So I'm not going to write out every single one, because as we know, step 1 is our balanced chemical equation. So in this case right here, our balanced chemical equation is we had our scandium chloride plus our silver nitrate. So this is a double replacement reaction. So scandium and nitrate are going to pair up now, and then silver and chlorine. Now we don't know the state of that, so we're going to have to check. And then we get silver chloride. And same thing, we don't know the state. So with these here, we are going to have to check their solubilities, because one of them should be a solid, and that is our precipitate. So in order to check, go to our data booklet. Go to your solubility table, just like this one right here, and we check. So first I'm going to check scandium nitrate. So our nitrate is right here. Most things are soluble. We'll notice scandium nitrate does not go up here. So a carbonation of scandium nitrate is very soluble. Awesome, so that is aqueous. Our next one, we had silver chloride. So our chloride ion is right here, and silver ion is down here, meaning it is slightly soluble or solid. So the combination of silver and chlorine is going to be our precipitate. So for scandium nitrate, AQ, silver nitrate, solid. And of course, we do need to balance this reaction as well. So in order to do so, we need to stick a 3 in front of silver nitrate and a 3 in front of silver chloride. And last but not least, following all the steps of our stoichiometry as well, it's good to highlight our wanted and our given. So obviously this is being produced as a solid, so this is our wanted. And the thing that we're given was our 28 grams of scandium chloride. That is our given. And same thing with the molar masses. You can write this above if you want to, but I'm just going to use the molar masses when I need to. So our step 2 is find the number of moles of our given. So number of moles of our given is equal to mass over molar mass. So our mass was 28.0 grams. Now the molar mass of scandium chloride, SCCl3, it's 1 scandium and 3 chlorines. When you add that, you get 151.31 grams per mole, and we get a molar mass of the number of moles, 0.185051 moles. So then we move on to our step 3. Our step 3 is find a number of moles of our wanted using our mole ratio. And it's that equation right here. So we take our 0.185051 moles, and we multiply by the coefficient of our wanted, which is 3, over the coefficient of our given, 1. And we get 0.55515 moles. And finally, step 4 for our stoichiometry, solve the question, and our step 4 is mass is equal to number of moles times our molar mass. So our number of moles, 0.55515 moles. And our molar mass for silver chloride, remember, it's just the molar mass of 1 silver and 1 chlorine. Do not use that coefficient in front. You should get this as your molar mass, and we get 79.6 grams. Now, because it's asking for what mass, obviously we are going to report this with the correct number of significant digits, right, which was 79.6 grams. Now, this is our prediction, so this is all the stoichiometry stuff that we've done last class, or last lesson, right? So nothing really new here. Now, the analysis is going to be new. So remember, the analysis section, this is what we actually collect. So this is what we actually collect at the end of the experiment. So what we have right here is we have to look at the evidence. So student weighs a filter paper to be 0.59 grams. Then they filter the precipitate and get 78.59 grams. So this mass right here is the mass of the precipitate. So I'm just going to label PPT for precipitate, plus the mass of the filter paper, so FP. So it's two of them together. So we do need to be... there is a formula, like there's not really a formula for this, but if we really want to, so just mass of our precipitate, PPT, is equal to the mass of the precipitate plus the filter paper minus the mass of the filter paper, right? That should make sense because when we weigh out the precipitate and the filter paper, we had 78.59 grams, and we knew the filter paper before weighed 0.59 grams, so if we subtract one from the other, we're going to get the mass of the precipitate just being 78.00 grams, which is exactly what we need. So that is exactly the mass of what we actually collected there. So finally, our new step is the evaluation. So how close were we to the actual value? So that's where we need to do our percent difference is equal to. So we get the absolute value of our experimental minus our predicted all over our predicted times 100%. So our experimental value is, of course, the one that we actually collect, right? So that is our 78.00 grams minus our predicted, that's our stoichiometry, 79.6 grams, all over our predicted 79.6 grams times 100%. And when we do this, we get our percent difference should be equal to 2.01%. And of course, 3 significant digits because that's what we have up at the beginning of the question. And of course, even this one right here, our 79.6%. So that is how we go through solving our prediction, analysis, and evaluation stuff. So the prediction should be nothing new, especially if you followed on around last lesson, and then of course you did a lot of the extra work in the workbook because you would have lots of practice with the gravimetric stoic. So now really the only new steps is the analysis portion, so figuring out what is the actual mass we collect and using the percent difference. So just like last time, I'm going to go over example 2 in fully fully with you guys as well, and then just kind of put up the answers for the example 3 because that's one that you should hopefully be able to get on your own as well. So let's have a look at example 2. All right, so example 2, it says, in order to collect silver ions from a reaction that did not go to completion, a laboratory technician mixes 25.00 grams of magnesium iodide in enough water to dissolve it completely, then mix that solution with excess silver nitrate. So of course, our experimental design, this is what we use for our prediction. Remember, our evidence, this is what we use for our analysis. So I'm going to ignore this stuff right here, just for right now, and do the prediction section. All right, now where we already done a bunch of gravimetric stoichiometry questions, you should be able to get this on your own. So I want you to pause the video and see if you can fill this out on your own. And I'm just going to pop up the answer here now in 3 seconds. And of course, the prediction section should look like this. Our balanced chemical equation, number of moles were given, number of moles were wanted, and of course solving for the mass. I just kind of wanted to not really fly through that one, but we've done a bunch of these here, so hopefully you're getting much better at them. So I just kind of want to go towards, because the whole idea of this one is looking at the analysis and the evaluation sections, because these are the new ones. So the evidence. So what we have right here, before filtration, a piece of filter paper used to collect precipitate weighs 1.15 grams. After the collection of precipitate, the filter paper and the precipitate weighed 41.88 grams. So that's in our analysis. Basically what we have is mass of precipitate. Just going to shorthand precipitate to PPT. So remember, we are going to take the mass of our precipitate and our filter paper and subtract just the mass of our filter paper. So that means we take our 41.88 grams from the question, subtract our 1.15 grams, and we're left with 40.73 grams. So just kind of highlighting, remember this is our predicted, and this is our experimental. Because reading the question, this is what we actually get. Now, of course, remember our evaluation, this is also a new one, where we go percent difference is equal to the absolute value of our experimental minus our predicted all over our predicted times 100%. And of course, putting that in, that means we have 40.73 grams minus 42.21 grams all over 42.21 grams times 100%. And we get our percent difference is equal to 3.530%. And of course, this is 4 significant digits because of everything else we had was 4 significant digits. That was the lowest number of significant digits that we had in the question. And that is how we get those. So, of course, with the next one, example 3, definitely want to try this one on your own as well. Just kind of reading through. So this one here is a little different where we don't have a filter paper, but what we have is the heating up of malachite. So this is the chemical formula for malachite. It is decomposed into copper, 2 oxide, carbon dioxide, and water. And because we're heating it up, it's going to be H2O gas. Right, so even though this is an atypical reaction, so it doesn't fall within one of our 5 named reactions, the fact that we have our reactant and it's telling us what it is decomposed into, you can definitely write out the chemical reaction for this one. We even have the mass of malachite right here, and our evidence after heating, the beaker has a total mass of 92.3 grams, where the original beaker weighed 28.5 grams. So there's enough here to get this right here. So same thing, definitely want you to try this one on your own. Of course, once you actually get it done, check the data booklet, the answer key just to make sure. But for evaluation, what you should get when you're done, percent difference should equal 11.3%. So keep trying this one until you get this answer. And of course, if you don't, if you want to see where you made it wrong, just kind of schedule either a Google Meet with me and we can go over it, or just have a look at the answer key and see what I have done. But you will notice everything is still labeled out exactly how I've been doing it so far with all these here. So of course, that's the end of this particular section. So our next one is going to be next week. We're going to look at gas stoichiometry, solution stoichiometry, and percent yield. And that will end off our different types of stoichiometry. And of course, we are getting really close to the end. So just make sure to try the CYU book with these here. Make sure to master the gravimetric stoichiometry first and the percent difference. So in this way, when we get into the different other types of stoichiometry, it'll just make it a little easier for you to transition between the gas stoichiometry and solution stoichiometry if you have your gravimetric one mastered. So anyway, make sure to work, and I'll see you guys next week for your next 3 lessons.